In this video, I give you an introduction to time and space complexity for the layman programmer. Hey, my name is Khan. I'm a software engineer at a startup and I've worked for companies like Sony and Google. Back in early 2016, I started out as a beginner to coding, not sure how to progress or make my way into industry. But by 2018, I was making over $180,000 at Google as a software engineer. There are a few key pivotal principles that I learned along the way that I say most contributed to my success and the path that I was able to take on this journey. In this video, I want to introduce you to one of those key principles, the basics of time and space complexity. Or put another way, a way to describe the performance of our algorithms. This is a topic that you should have a strong grasp on since it deals with the performance of the code that we write. So I'll give you the 80-20 of these concepts and show you the basics you need to know to be a productive programmer right here in this video. Okay, let's dive in. Time and space complexity is about measuring the efficiency of our algorithms. So that brings about it another question. What is an algorithm? Put simply, an algorithm is a list of steps or a set of instructions for a machine. When we have to instruct the computer to split a sentence string into an array of words, that's an algorithm. When we have to tell the computer how to find the common denominator between two numbers, that's an algorithm. Pretty much all of your programming is riddled with algorithms everywhere, left and right. And the word complexity, as it relates to algorithms, is about how an algorithm performs as the size of input increases. And more specifically, it's talking about what happens when the size of input approaches infinity. First, let's explore time complexity. Time complexity is about how long an algorithm takes to perform as the size of input approaches infinity. This will begin to make a lot more sense as we dive into an example. Let's say that we're given a sorted list of numbers and we want to write an algorithm that returns a Boolean if any two numbers in that list adds up to 10. A brute force approach would be to have an outer loop that visits each item in the list and an inner loop within the outer loop that looks at all other numbers in the list. This means that for the number 0, we check all other numbers, 3, 4, 7, and 11, and see if any of these combinations sum up to the desired target of 10. We would then iterate the outer loop and repeat the process to check all combinations that include the number 3. This approach ensures that we see all possible combinations in the list. This means that for an input size of 5 numbers, our algorithm, in the worst case, will iterate a total of 20 times. 5 numbers for the outer loop and the other 4 numbers for the inner loop. Do you notice the inefficiency? There are combinations in this list that are repeated. In fact, everything is basically repeated. We can do better. Now, another algorithm we could use is to look at the list in a different fashion. Because the numbers are sorted, we know that anything to the left of a number is smaller than that number, and anything to the right of a number is larger than that number. We can take advantage of this characteristic to logically deduce that some combinations do not have to be checked. For example, if we're looking at 11 and 0, there is no point in checking 11 and 3, 11 and 4, and 11 and 7, since 11 and 0 already sums up to be a number larger than our target of 10. Moving this left pointer would only increase the sum. So for our algorithm, we could iterate 2 pointers starting from the ends of the list. The first pointer dictates the number we are on, and the second pointer dictates a potential pair. We have the choice of moving the left pointer inwards or the right pointer inwards. Given this situation, it would be silly to move the left pointer to 11 and 3 because we know that moving the left pointer to the right increases the total sum to some value equal to or higher than 11. So we can logically deduce that the only right choice for the algorithm is to move the right pointer inwards, potentially decreasing the total sum from 11, which has a shot at landing at 10. However, moving the right pointer results in a sum of 7, which is less than our target total of 10. So we know to move the left pointer inwards on the next iteration. Once we move the left pointer to the right, we land on 3 and 7, which matches our target sum of 10, and the algorithm can stop. Now with this algorithm, if you follow the logic, it would be pointless for the left and right pointers to cross paths because once the pointers cross, everything becomes a repeat of a previously seen combination. So the algorithm should end when the pointers meet at the same index. This means that our pointers combined will only ever visit all of the numbers in the list once. We'll have exhausted all potential combinations in less iterations by taking a logical shortcut and not checking unnecessary combinations compared to the first approach. So with this approach, we have to visit a list of 5 numbers up to 5 times plus one last time until the pointers meet. All right, so let's recap what we've covered so far. With this first approach, when our array size was 5, we iterate 5 times for the outer loop and 4 times for the inner loop, resulting in a total iteration count of 20. If we increase the input to 10, we would iterate 10 times for the outer loop and 9 times for the inner loop, resulting in a total iteration count of 90. More generally speaking, given an input size of n, we are iterating n times n minus 1 times. With the second approach, when our array size was 5, we iterate a maximum of 6 times until the pointers overlap. When our array size is 10, we iterate a maximum of 11 times until the pointers overlap. More generally, given an input size of n, we are iterating n minus 1 times. However, remember that algorithmic complexity has to do with what happens as the size of input approaches infinity. So let's observe the pattern of what happens as our input increases by an order of magnitude from 5 to 50 to 500 and 5,000. With approach 1, we go from 20 iterations to 2,450 iterations, 249,000 iterations, to over 24 million iterations by the time we hit our input size of 5,000 numbers. With approach 2, we go from 6 iterations to 51 iterations to 501 iterations and 5,001 iterations. As you can see in this table, as the input size increases, the rate of change in the number of iterations performed is drastically different. Now remember in the very beginning that I mentioned that time and space complexity is about approximating the efficiency of our algorithms. We actually don't care about the exact numbers here. What we care about is the general pattern in how quickly the number increases. Or put another way, we care about this rate of change. So when we talk about the complexity of algorithms, what we care about are orders of magnitude, not the exact number of computations. So the difference between n times n minus 1 and n times n, or n squared, is negligible, since we're talking about n approaching infinity after all. Same thing goes with approach 2. n plus 1 is approximately the same thing as n, since we're talking about such a big input size that that plus 1 does not matter. So we can simplify the approximation by simply stating that the first algorithm has a complexity of n squared, and the second algorithm has a complexity of n. Now there's a specific way we denote that we're talking about the complexity of an algorithm, or the approximate rate of change. We use something called Big O notation. With Big O notation, we notate our respective algorithms as having an O of n squared and O of n time complexity. The O is just an indication that we're using Big O notation. The actual complexity is dictated by what's inside the parentheses. Being able to characterize algorithms this way is important because it gives us the necessary understanding of how an algorithm will perform as we put our systems under distress with more traffic and more users. Now it helps to visualize Big O notation using a coordinate plane with the x-axis being our input size and y-axis being our unit of measurement, iterations in the case of time complexity. From our earlier examples, the O of n squared would look like this curve when visualized on this graph, and the O of n would look like this when visualized on the same graph. This can quickly give us an idea of which complexities are preferred. Now there's a bunch of different complexities like O of 2 to the nth power, n squared, O of n log n, O of n, O of log n, and O of 1, and a bunch in between. But because this is an introduction, we'll stick to the basic ones that help us understand the gist of this complexity thing. O of n squared, quadratic, O of n, linear, O of log n, logarithmic, and O of 1, constant. Once you have a grasp of this time and space complexity thing, you can come back and study the other ones later. In the previous examples, we saw the behavior of a quadratic and linear algorithm. Let's explore the logarithmic complexity next. The best example to understand this is to try to think of an efficient algorithm to find a word inside of a dictionary. If you were searching for the word dad, you'd probably flip to some area towards the first quarter of the dictionary to find the words that start with the letter D, right? And then you'd skim pages to the left since DA is one of the earlier words that start with D. Without knowing it, we're performing a highly efficient searching algorithm. If you think about it, it's more efficient than a linear search where you start at the first word of the dictionary and keep looking until you find the word dad. Now, if you were to tell a machine to perform this algorithm, we need to give it a repeatable set of instructions. The idea for the algorithm would look something like this. 1. Look at the middle word in the dictionary. Split the dictionary into a first half and second half. 2. If the target word comes before the middle word, split the left half into half again and repeat. 3. If the target word comes after the middle word, split the right half into half and repeat. Keep splitting the possible words in half until we find the word or there are no more pages to search. With this algorithm, as the number of words in the dictionary increases, our algorithm gets more and more efficient relative to the number of words. We only need about 13 cuts to find any word in a 10,000 word dictionary. This is because each iteration cuts the total possible options by half. That means that in a 1,000,000 word list, our first iteration gets the list down to 500,000 words in one shot, then 250,000 words in the next shot, then 125,000 in the next. It only takes 3 iterations to get from 1,000,000 possible options to 125,000 possible options. This pattern is called a binary search algorithm. And a binary search algorithm has a time complexity of O of log n. We like logarithmic algorithms. They are highly efficient and scale very well as the input size approaches infinity. And this is what the graph looks like with our logarithmic function in it. But you know what's even more efficient? Constant time algorithms. Constant time algorithms are performed in constant time. This means they take the same amount of time, irrespective of input size. We call this O of 1. This is our favorite type of algorithm since it means we don't need to worry about that particular algorithm degrading system performance and being a bottleneck, despite increases in traffic and users. Some examples of this would be accessing an item in an array by its index, or looking up a value in an object by its key. These are performed in constant time. It doesn't matter how many items are in the array or how many key value pairs are in the object. Now, if you're interested in learning why these can be performed in constant time, that's a lecture for a different day on data structures. If you'd like to see this, let me know by commenting down below that you'd like to see it, and I'll look into producing it. Okay, so now you can make sense of this graph and see how each of these big O complexities affect performance as input size increases. Here's a note on space complexity. So space complexity is similar to time complexity. We're talking about the complexity of an algorithm, just in a different context. Time complexity is about measuring the speed efficiency of an algorithm relative to input size. Space complexity is about measuring the storage efficiency of an algorithm relative to input size. In other words, how much storage space, which we typically think about in terms of volatile storage or RAM, is needed to perform the algorithm as the input size increases. For example, if your algorithm has to copy an input array to return an output, you automatically have a linear space complexity at the very least. But if your algorithm only uses a single variable and a for loop over the array, it doesn't matter how long this input array is. You'll only ever need one variable, which means you have a constant space algorithm, or O of 1 space complexity. Why does this matter? Time and space complexity matters because as the size of our inputs grow, a poor complexity will degrade the performance of our systems. In a real-world context, as our servers begins to handle more and more traffic, there's only so much we can ask it to do. A single machine has a fixed amount of CPU processing power and RAM, and we can overload the system by asking it to do too many things or asking it to keep track of too many things. Less efficient algorithms will cause this to happen much more quickly. Okay, so that's the introduction to time and space complexity. Let me know what you thought of this new style of video down below in the comments. If you liked it, then go sign up for my newsletter, thecommit.dev. I'm working on more, better educational content that dives deeper into technical topics to help you actually apply principles, establish sound mental models, and help you level up as a software engineer. So if you're looking for content similar to what you saw here in this video, I'd recommend subscribing to my newsletter. All right, happy studying, and I'll see you in the next video. Bye-bye.